going to teach us invariant measures and ergodicity of stochastic Navier-Stokes equation in the next some 6 or so lectures. So 3 or so lectures.
3.34 is what?
Okay. Thank you very much for coming after lunch to listen to me. And the topic is ergodic behavior. So you probably already know about invariant measures. And for instance, let's start with an example. dxt equals, let's say, minus 1 plus. And x0, let's say, is some z, which is independent of the Brownian motion, right? And alpha is a positive number. I'm sure all of you have seen this. Do you know the name for this process? Except T? Right. Ornstein-Uhlenbeck process, right? Okay. So this is a stabilized process actually. Brownian motion, has infinite speed and therefore cannot really adequately represent the motion of a particle, right? And therefore there is a brake. You apply the brakes here. And why do I call it as a brake? Because alpha is positive and therefore there is a negative drift, right? So if x is very large, this will push it down. And if x is negative, right, then the minus alpha will take it out, take it upwards, so that the process doesn't go hurtling down full speed to abysmal depths. And therefore, you can expect some kind of a stationary measure, right? And okay, supposing, what is xt? Do you know the solution explicitly? This is just a linear term. Therefore, all that it can contribute is like an exponential factor. And then this is the time varying part. Therefore, simply do the, you got to take care of the z also, right? E to the minus alpha t plus integral 0 to t, e to the minus alpha, t minus s, t minus, right? So that's a no-brainer. One can do it readily. And I had told you that z is a random variable independent of Brownian motion, which is how the Ito integral equations should be. Otherwise, you'll get into problems of non-adaptedness. What is the distribution of x sub t? X sub t is this is a deterministic quantity. Any linear combination of normal random variables is normal. So integral is nothing but a combination, right? When the integrand is deterministic. So would you say that this is normal? xt, the distribution of xt is normal, right? And what is the expected value? First of all, tell me what the expected value of this is. That's 0, right? So you get only from here. And how about the variance? Because normal distribution is characterized by the mean and the variance. Therefore, if you find the variance, z is independent of the Brownian motion. So variance is simply add up. And therefore, you'll have the variance of z, e to the minus alpha t, e to the minus 2 alpha t, plus, and then how about the variance of this part? It's simply, okay, first I'll write down as an integral t minus s ds, right? So we want to make this distribution to be not dependent on t. So how to make this part not depend on t? So what would we expect of the z? You have to make it 0, right? Good, good. So we want expectation of z to be 0, right? And then this part should also be, let's calculate what this is, okay? So this part is there, and then if you calculate this, what happens? Change the variable and do the obvious, you get this, correct? And here also there is a e to the minus 2 alpha t, right? And then variance of c. So how to make it independent of t? You want to cancel this with this, right? So what should the variance of z be? There is a negative 1 over 2 alpha, so you want it to be 1 over 2 alpha, right? So if you expect this to be 1 over 2 alpha, then this cancels with this negative part, so leaving you just with 1 over 2 alpha, right? Then, so therefore, if z is normal with 0, 1 over 2 alpha, then what happens to xt? Maybe this expectation of z is 0, therefore this is 0, and the variance is the way we chose it, and the cancellation will give us exactly 1 over 2 alpha, right? So why is this so nice? The initial distribution is normal 0, 1 over 2 alpha, and the same persists even at all, for all times. So this is a kind of stabilization, if you want to call it, right? Or stationarity. That's the correct word. So stationary means the distribution is invariant over time. It doesn't depend on time. So this is something I think you would have all studied in basic stochastic analysis, right? Wherein nothing much is needed except a Wiener integral. It's not even an Ito integral, right? And so we call this distribution, normal 0, 1 over 2 alpha, to be the invariant distribution for this process. That's all there is to it. So you should know where to start so that the distribution remains the same, right? So 1 over 2 alpha is the invariant or stationary. You can call it either way. Dubh-Dinkin. Right, right. There is always cause and consequence, right? So several things depend on how you choose the initial variable.
Alpha non-zero doesn't work. Alpha is 0.
Right, right. That's right.
Very interesting.
Exactly. If alpha is 0, then it's just the Brownian motion, and it's wild, right? You cannot really control the behavior of it. So that's why Ornstein and Uhlenbeck came up with this process. Namely, this is like applying the brakes so that nothing bad happens. Okay, so this is something I thought you may all know about. Constant. Yeah. Right. Otherwise, it will be like an integrating factor if it is alpha of t dt, right? Yeah, xt dt. Okay, so this is my example 1 to show you that you already knew what an invariant measure is, right? Example 2.
Should this always be a normal distribution?
It doesn't have to be. In this case, it's normal because of the simplicity. Yeah.
What if you assume say uniform?
Oh, then it won't, you can work it out. It won't come out to be because a linear combination of uniform distributions is not uniform. Yeah. Example 2, I have used the word ergodic. So does that ring a bell? Do you all know the basic ergodic theorem for Markov chains? No? Okay, if you don't know, I'll skip it. I can tell you, unless you want to know about it. What is a Markov chain? Markov chain is one, let's say, a time homogeneous Markov chain. That means it goes from I to j with a probability called, which we denote by Pij, right? So if you want to go from I to j, then the probability of this is Pij. So this is time homogeneous. So I didn't tell you from what time to what time, right? But this is in one step, okay? So otherwise I'll put like this, so to denote several steps. So the Pij's, if you combine them, then that's called the matrix P. That's called the transition probability matrix, right? Some of you seem to know it, right? So it's the one-step transition probability matrix, right? And the theorem says, I'll go actually to the finest theorem about the ergodic behavior here. If X sub n is a Markov chain with transition matrix, that's what the name is for P. It's good to know this because from embedded in a lot of Markov processes, there are Markov chains forming certain what we call as skeletons. With transition matrix P, that means one step. It gives you the dynamics of going from state 1 to state 2 or state 5 to state 3, whatever. If the Markov chain is irreducible means what? Irreducible means there is the state space and you can go from any state to any other state in some number of steps, all right? Everything is accessible. If it is irreducible and positive recurrent, then there exists a unique vector pi such that pi is. So here pi is the invariant measure. So what has happened is, let's say you have pi 1, pi 2 and so on, right? And then this Pij matrix, again it comes out to be pi 1 and so on. Yeah. Right, it's a time homogeneous Markov chain, correct. Yeah.
What is recurrent?
Positive recurrent means you should be able to, there is a waiting time that you need to go from I and come back to I. That waiting time is finite, and also the expectation of the waiting time has to be also finite.
It must always come back.
Yeah, it must always come back. So if it always comes back, that's called the recurrence. Positive recurrence means the expected time that it takes is also finite. So, yeah. The Markov chains are always in discrete time. Yeah. If it is in continuous time, we call it Markov processes. I'll tell you about Markov processes. Irreducible means after some large n, it becomes positive. Yeah.
You can. Yeah, well, that's the PAJ.
Right. Yeah. So this is. Oh.
Don't use that.
That is better.
This is better, huh? Okay. So where is the ergodicity, you may ask, right? This is only an invariant measure pi. You can see that pi is an invariant measure because if you start with pi, then in the next step again, the distribution of the states is again pi 1, pi 2, pi 3, and so on. All right? If you just do the matrix calculation, this is what 1 cross n, let's say. This is n cross n, 1 cross n. Okay, everything is conformable for multiplication. Now, there is one more part to it, which is 1 over n times summation, j varying from, or k varying from 0 to n minus 1, let's say, of f of xk converges almost surely to summation ii f of I over I. So this is really a phase space average, right? So if you think of pi, summation of pi I actually is 1. Okay, I forgot to say that summation of pi sub I is 1. So what here, what it says here is that initially, meaning your x sub 0 has distribution, namely probability that x sub 0 will be 1 is pi 1, probability that x sub 0 equals 2 is pi 2, and so on. Then the same distribution is there for x1, and then for x2 and x3 and so on. That's exactly what this equality means if you work it out, right? It's just 1 minute exercise. And this can be, let's say, if you write it like this, that's fine. Correct? So this is called the basic ergodic theorem for Markov chains. Do you all remember who proved it? Huh? Yeah, Markov is more general. This is Erdős. Feller. Erdős, Feller, and Pollard also told me he did it also. So put his name also. I think his name is there, right? Feller, Erdős, Pollard, or whatever. So Pollard is a mathematician, and I asked him how he came to work on it, and he said Feller told him to work on it. Okay, so that's how he got to this important result. So this is an almost sure result. This is an ergodic statement. That means there is a time average. Time average converges to what we call as a phase average, meaning it's an integral with respect to a measure on the state space. State space simply means the set of values taken by the random variables. Here it could be, I call them as I and j, right? Wherever you pick them to be, that's the state space. Okay, you haven't seen, maybe example 3 I'll try. Maybe you would have seen this. How about independent identically distributed random variables with finite mean? Okay, so x1, x2, IID, expectation of x1 is, let's say, m finite. Then do you all know a result about this? Where does it converge? Expectation of x1? In what sense? Is it in the sense of L1, LP, in probability, in measure? Almost surely? Almost surely, right? Whose result is it? Huh? Right, Etymology gave a nice proof, but Kolmogorov's strong law of large numbers.
Yes, it not assume just L1.
Right, that's right. True. That's right. But really, we call it as Kolmogorov's strong law of large numbers. Strong law of large numbers. Okay, so it's always an almost sure statement, and it is simply the arithmetic mean. You can think of the j going from 1 to n as the time going from 1 to n. So you are averaging over time, and it is expectation of x1 which is really what? Integral of x1 mu, or where do you want to put d, dx1, let's say, where mu is the distribution of capital X1, right? In which case, you can see that this is the measure I was telling you as like this, right? Namely, it's a measure on the state space of the dynamical system. Here, of course, it's all IID, but still you can consider it as a dynamical system under the shift transformation, all right? So this is similar to what we have here, right, in spirit. Almost sure convergence, time averages converging to phase mean. That is integral with respect to a measure on the state space, right? Okay. So this is also a ergodic statement. So ergodic means time averages converging to a phase space average. All right. Note that even here, this mu is invariant, right? Because the distribution of this is mu, and so on. So it's invariant. Just as the pi that I erased was invariant. So first you got to find an invariant measure, prove that it is unique, and then go for the ergodic statement. Either in the sense of mean ergodic theorem of von Neumann, in the L2 sense, for instance, or you can go for the almost sure statement. All right? Ergodic theory didn't start just like this, like I told you. Rather, it started with a dynamical, looking at a dynamical system. X is in the state space, let's say. Fix a point in the state space and then see the evolution of this path, right? So t sub t x. So this little x goes to t sub t x by time t. So if you put it all together, so t sub t denotes the random dynamical system that we have, and t sub tx, what should we call it? We may call it as probabilis as sample function or something, because x is fixed, right? But this is usually called an orbit. Look at the orbit. And let's say that it is, nothing happens just with time. So t sub tx dt possesses. And t sub 0 is, let's say, just the identity. All right? So it looks like something familiar to us. So this is how the dynamical system evolves according to this transformation t sub t that goes from the state space to the state space. And then Boltzmann came up with a conjecture, bold conjecture that if take any orbit, and if it goes everywhere, nook and corners of the state space, and doesn't leave anything untouched, then it has to be ergodic. The system has to be ergodic. All right? So ergodic means what? Summation. I made it all f of ts x, right? ds converges almost surely to some f bar, which is an integral with respect to the state space, all right? Irrespective of which orbit you take. So this was Boltzmann's idea that, and it is called as the ergodic hypothesis. And the system that he took was the Hamiltonian system, so that derivative of the Hamiltonian with respect to t was 0. Okay, that's the kind of system that he took. Therefore, a Hamiltonian is just the addition of all the energies, okay, the kinetic energy plus the potential energy. Therefore, since the derivative of h with respect to t is 0, h remains as a constant, right? And therefore, it doesn't leave the energy surface, so to say. So within the energy surface, it has to have a phase distribution, an invariant distribution, which is actually ergodic, right? That was his idea, and it is not wholly true. Later on, mathematicians had to find sufficient conditions under which it is true, all right? I can tell more about this later if you are interested. I didn't tell you anything about T sub T being a measure-preserving transformation and so on, since that would take us somewhat far off from the field. Not too much, but I have more things to say. There is a method to my madness. Okay, so all these statements are about convergence of time averages to an integral with respect to a measure, right? And therefore, what Kolmogorov conjectured was for us to take d du of t with respect to t plus mu a u of t plus b u of t. You know the a and b, where a is the Stokes operator and b is the nonlinear term in the Navier-Stokes equation. And he said put some w dot of t, meaning derivative of w with respect to t. This is called forcing by white noise. So whether white noise comes in a PDE as due to random disturbances and modeling, or as a control term, it's up to you how you want to use it. So what he said was consider the Navier-Stokes equation. Of course, I had to also write that del dot u equals u on the boundary of G is 0. All these kind of things, okay? U of 0, it's number of it. So consider the Navier-Stokes equation that Professor Sridharan introduced today, and it is in this notation, right? It can all be written in the integral form, maybe that's better, right? And then look at it. It won't be just dw by dt, but w sub t in the simplest case. Namely, you just put a Wiener process on the right-hand side. And he thought that this may be solvable, and one can get an ergodic measure, all right? Invariant measure first to start with. You need invariant measure and uniqueness of the invariant measure, and then talk about ergodicity, right? So this was conducted by him in what? Some Petrovsky seminar or something, right? That's what Vishik and Puzikov say. And therefore, it's worthwhile for us to go to this level, but not today. I just am advertising where we can go. So already from one dimensions, now we have come to function space, right? Infinite dimensions. But then we'll now take several steps back and then see how to prove existence of invariant measures for infinite dimensional systems. So now we'll go a little bit pedagogically and let E be the state space. All right. E has some topological properties, such as, if you want, it can be a complete separable metric space, or it can be, or just take E to be RD. It doesn't matter. Okay. For example, E is RD. complete separable metric spaces tie in very well with weak convergence of measures, all right? Completeness we all need because we may just get a Cauchy sequence and we want it to converge. So it's not a big thing. Separability is very important. For instance, where do we first use separability in probability theory? It's difficult to answer this kind of a question, right? Because it seems so basic. Even if you have, let's say, two random variables, and you put them together and you want to call it as a random vector, that means the Borel product of Borel has to be the Borel in the product space, right? That won't happen unless you have a separable space. Yeah? So very basic. So we are not asking too much if he is a complete separable metric space, all right? But for now, you can even think of it as RD. Let xt super x, okay? It is all indexed by x member of E, be a family of Markov processes, time homogeneous Markov processes. Homogeneous Markov processes. On a space omega f, okay? Oh, I wrote a long sentence there. Yeah. Borel's, right, yeah. So let us consider a family of, the little x can be thought of like the starting point or something, right? Which is like really what it is. So when I put a superscript, note that x super 0, sub-0 super x is actually x. That's all it is. So the superscript denotes the starting point. And they are all Markov process. Markov processes simply means that it has some forgetfulness, right? Not total amnesia, but partial. Namely, it forgets the past but remembers the present. So now let's find out what the transition probabilities are, right? So let P sub x T of B. That will denote the probability that this x sub Tx takes values in B. Probability. So this is a definition, right? There is only a P there, right? Namely probability measure, but P sub x is being defined here. And T is any greater than or equal to, meaning a non-negative number. B, member of, let's say, where would it be? It is all taking values in, right? Let's call it a script E, which is the Borel sigma field for E, right? So far, all right? So you take one of these processes and you want to know its distribution. That's precisely the distribution, right? I don't mean the cumulative distribution, just distribution, and that's given by P sub x of T. That's my notation. So there is nothing to think about there, right? So you can arrange matters such that this P sub x of T B, when you change the B as a function of this, these sets B, it's a set function, right? Set value, what is it called? Set function? Yeah. And it's a measure, probability measure. But if you fix the T and the B and look at it as a function of x, it's actually a measurable function of x. Now, where? law of Xi, or Xi as distribution, right? Probability distribution given by some nu, let's say. Then how to write probability of XTXZ, member of B. Z is independent of everything else, right? So you can actually put Z to be just little x and then look at it. And then little x, they have to be distributed according to the nu, right? So this is integral dx of t d mu dx. Is that agreeable? That's easy. So take all these kind of processes which start at little x and then see at time t the probability that they will be in B, and then integrate with respect to the nu, because nu is the initial distribution, right? So it is nothing but conditioning if you want to think of it that way. Okay, so these are all not for you to think too much about, because this is simply the notation, and I'm just saying standard things here. Okay. Define S sub t phi of x to be integral. I'll write it in terms of expectation. Expectation phi of x dx. Let's pause and think about this. Okay. So here is I'm defining a map called S sub t, and phi is, let's say, a bounded Borel measurable function, for instance, or it can be a continuous bounded function, whatever you take. So S sub t phi of x is the initial variable, right? The way I can define. The superscript is always the initial variable. And I'm measuring what happens for such a process according to this, in the dynamics is according to this x dx. Then S sub t is actually the semi-group generated by this Markov family. You can prove that it is a semi-group. And why is it a semi-group? What is the fundamental equation that you have for Markov processes? Chapman-Kolmogorov, very good. Have you all heard of Chapman-Kolmogorov equation? That's the first thing that we learned, right? Even in Markov chains. And what it says is, I don't need this. Right? I want to go from, let's say, some state x to some state z, all right, at time t plus s. So Chapman-Kolmogorov equation says, well, you can go to y and then y to z, or you can choose some other path that's there, in which case this becomes the y, and then you can go to z, and so on and so forth. Right? So you can split the transfer mechanism into two parts. That's all there is to it. And that's what we need to prove that ST is a semigroup. Let's say probability, or rather PT plus S. First, let me do this. Going from x to z, right? X to B, let's say. I want to go somewhere here, maybe. Then how can I split it? It is PT of x dy. That gives me that in time t, I go from x to some y, and then in the remaining time, where do I go? this is not however, pxt, right? I shouldn't change my notation. From x to y, and then I go from y to, in S units to v. And I have to exhaust all my paths, right? So y can be wherever, right, in the whole state space. Therefore, I get to write it like this. That's all there is to it. Of course, this is a funny way to write, yeah, because here is the measure and then the integrand is here. That's all right. Yeah. You can always transfer it. It's kind of strange. So this is called the Chapman-Kolmogorov equation. And use it. And what do we want to prove to say that it is a semigroup? You want to consider S sub t plus S, right? So you will put a t plus S. Then write it in terms of the p t plus S. And then break it up to t and then to S. Do Fubini. You can do Fubini, no problem, because everything is bounded. Right? And you get the semigroup property. I'll leave that as an exercise, right? If you want to, we can do this in the tutorial. So the exercise is show that St plus S phi and S sub 0 is just I, namely the identity. Okay, I'll also put that. Any questions so far? Okay. So this is our dynamics, akin to what I told you about Boltzmann and so on, right? That was the Hamiltonian dynamics. This is for the Markov family that we have. And the dynamics is given by S sub t and all that, right? So make it work on continuous function, bounded continuous functions, for instance. Then it's a C0 semigroup. You can. I'll also add some more things to this exercise. S sub t of the function which is always 1 is 1, right? And S sub t is also a contraction. All right, now we are in business. I'll define for you what an invariant measure is. And we will, okay, this is better, I guess. Definition of an invariant measure. In the first three examples, we had invariant measure, right? So, so mu is an invariant measure. A probability measure mu is an invariant measure. If, for the family, right? For S sub t, whatever. For S sub t. Yes. There are several ways to write it. Can you suggest one way? How about in terms of x0 and so on and so forth? If the law of x0, L, script L means the law or distribution. Okay, probability distribution of x sub 0 or if you want to call x0 as z, you can even put z and then z, whatever you want, because the superscript simply means where you started, so the distribution doesn't change with time, right? Or you can say the following, that is, it has to be mu, right? Because I had to connect it to mu.
Find a xi such that it satisfies.
Correct, exactly, yeah. That is probability. Mu dx. So this is the law of xc, okay? Should be equal to, correct? I just wrote it in the reverse way. So this actually is here, and this is here. Okay, so another way to write it is as follows. How about, so that is, that's it. Okay, this is the nicer looking of the, well, I like this one, but being a probabilist, but then connecting it to semigroups, the star is very nice, right? You all got it? This, it is exactly from here to here, so nothing else. So it's almost like a fibering, you know, there is this measure mu, take mu to a condition, right, such that you are at little x, find the expectation, and then say, oops, I did it for a little x, let me average over the mu dx, that's all. Okay. Before I state the next theorem, which is very easy to prove, so I'll prove it. How many of you know about weak convergence of measures, probability measures? Oh, excellent. Okay, then I had to be careful. Some people know, right? Among the students. And so, before the result, let me have one more definition. Okay, so I get defined what is known as an invariant measure. That means it doesn't change with time once you start correctly. But then to start things correctly is very hard, right? It is like saying, okay, you be an excellent student, then you will remain excellent. But then the question is how to be an excellent student, right, initially. So that's hard. Or you be in Princeton, then you'll always be in some elite company or something. First step is, right? It's like what Professor Sridharan said, who is to tie the bell, right, to the cat. Yeah. Yeah.
Before you go on, in fact, you didn't say for what field you define this.
You are right, absolutely right. Yeah. For all phi, actually CB is enough. CB phi. For all phi, remember CB phi. Okay, here are two more things which will look right now bizarre, kind of bizarre, but I'll explain to you. If S sub t maps continuous bounded functions to continuous bounded functions, all right? So it doesn't spoil the continuity and boundedness. Boundedness, of course, is there, but continuity is, right? Because S sub t, from phi, it becomes S sub t phi. That's another function, right? So S sub t takes phi, right, to another function called S sub t phi. And then you do this, right? If it is little x, okay, if you want evaluated x. So if S sub t goes from CB to CB, then S sub t is called, the semigroup is called Feller. Of course, Feller is the name of a probabilist, right? How can you call something else as Feller? Well, what is Feller semigroup, okay? S sub t goes from B sub B. What is B sub B? Bounded Borel measurable functions. Okay. Functions. To CB. So it's smoothing. That's not a strange thing. So semigroups are supposed to do that, right? Say the action of semigroup on a function phi typically is got by convolution, right? Convolution with the exponential term, right? If you think of it like that, right? The semigroup like that, and convolution is supposed to be a smoothing operator, right? And therefore, this is not a bizarre thing, right? And then we'll call S sub t as strong feller. So in the Navier-Stokes equations that Professor Sridharan discussed, S sub t would actually smooth it out, right? So let's say you work on periodic boundary conditions, then it goes to C infinity functions, right? And that's typical in diffusion problems, right? You start with even a dot, it becomes smooth infinitely, or whatever, right? Depends on the mechanism. Okay, so here are two statements. A semigroup is feller if it goes from CB to CB, and it is called strong feller if it goes from if it maps bounded Borel measurable functions into. Now with these, I'm ready to state a few things. One or two things I'll prove so that you get the idea of how the proofs are. And then we'll get sufficient conditions to show the existence of the ergodic measure or an ergodic measure. You understand? So the sufficient conditions have to be something that we can lay our hands on, namely you can compute something and actually verify those conditions, right? You all understand? You cannot say, oh, ergodic means take these time averages if it converges. That's just stating the definition again. You want conditions that are not too strong, not too weak, right? And ubiquitous in the sense that you can do it for several dynamical systems, which are random in this case. So first one, you'll all like this. What is weak convergence of measures? Let's say you have mu sub n converging to mu weakly. Actually, it's weak star convergence, okay? But probabilists call it as weak convergence. Let's say they're all probability measures, all right? You want a topology for the space of probability measures. So you put in all kinds of probability measures with state space E, where E is like RD, for instance, Borel, on the Borel sets. Now you have to give a convergence mechanism, right? There are so many ways to look at the distance between two measures. You can have the variation norm, or you can have the ones introduced by Kantorovich in the Montjampier problems, yeah, in the problem of shifting mass from one place to another place optimally, right? Let's say you have some sand hill or something, right? And you want to transport it 10 meters away in an optimal way. Do you take everything from the top and then put it at the bottom? You know, there is work involved, right? If you want to minimize the work, then you need to actually do it carefully. It's not obvious how to do it, right? So these are transportation problems, actually. Oh, there is a name for it, I forget.
Transport.
Optimal transport, right? Yeah, optimal transport. Right. So that's a Gangbo, right. Evans and others, yeah. And there you need certain distances which are called Wasserstein distance and so on. But for probability, if we say that mu1 converges weakly to mu, then what does it mean? Means you should all know, because you are in the land of Professor K.R. Parthasarathi, who wrote the first wonderful book on weak convergence, right? It simply means the following. Probably you know too many ways to describe it, so you're not able to come up with it, right? You have to look at continuity points of the measure and stuff like that. But ignore those. The easiest definition would be, cleanest definition would be, right, for all f c. That's called weak convergence of measures as n goes to infinity. Right? So he also has an excellent book called Probability and Measure, right? I don't know if you all read that.
Can you please write down CV in detail?
CD. Okay. Yeah. CD of E. Space of continuous bounded functions. Defined on E. Real valued continuous bounded functions. Okay? Defined on E. That, right. So F is in CB of E means F is going to be continuous bounded real valued. That's all I'm going to write here. Yeah, that's it.
From E to R and it's bounded.
Continuous bounded continuous. Right. So it's also real valued. Okay. That's what I want to emphasize. Okay. And how do you topologize? Well, with the soup norm, right? Now, what was I going to say? Yeah, the result. Let the semigroup S sub T be feller. So that's a very terse way of writing, right? Let the semigroup S sub T corresponding to this family of Markov processes XTX indexed by X be a feller semigroup. Like that, you have to write quite a bit. I hope you are okay with my way of writing. Otherwise, I'll be writing. Okay. Let ST be feller. Denote the distribution of xt c by, let's give it a name, okay, by mu t. Then it's easy for me, by mu t, where z, where distribution of z is given by some nu, let's say. That means it's the probability log, right? Probability distribution. If mu t converges weakly to mu as t goes to infinity, then mu is an invariant measure. For ST, meaning for the dynamical system. So you all understand this result, the very first result on existence of invariant measure. Yeah.
Is it the distribution of xi as mu or something? Mu and mu.
Nu, oh, I'm just calling it as nu. and then this limit as mu. That's okay, right? Yeah, there you can change it to nu. Then literally it will be a new definition, a new notation. Okay.
Whatever mu is, you always get a invariant.
Right, right. So nu, I'm just holding it as arbitrary, right? And if it the mu sub t converges to weakly to mu, then I get invariance of mu is an invariant measure. Okay. Since I haven't proved anything, I'll just show you some two-line proof. That's all it is. Maybe 3 lines. No? Okay. So that you will know the flavor of the proofs. You have to just do some small tricks, but always write it very naturally and then scratch around, you'll get it. Huh? Yeah. So mu t converges weakly to mu. What does that mean? Just now I erased, right? For any phi, I'll take another chalk. For any phi member of CB, meaning CB of phi, we have phi of x mu t dx, right? Converges to integral of phi of x dx as t goes to infinity. Agreed? So that's the definition of weak convergence. So mu t is the law, right? So you can write it as integral of phi of x. Do you all remember what the law is? It had p sub t and so on and so forth, right? Maybe for once I'll just write it here. Mu t dx, p sub x of t dy. I should also do a new dy, right? New dx. Remember? So that means I need a double integral there. That is, so I'm not writing anything new, converges to this limit. Right? Another way to write it would be s sub, in terms of s sub t, right? So that is s sub t phi of x nu dx converges to integral of p of x mu dx. I want all of you to understand, so I don't have to rush and then do something for myself. Huh? You all agree? Each step? So nothing to be afraid of, right? So this is the definition of weak convergence. Okay? And it is weak convergence that happens in what is the single most important theorem in probability theory? It's very central. Okay, central limit theorem, right? That involves weak convergence, right? The distributions converge. Okay? Yeah, same thing. Okay. And then I just wrote what is mu t, which was defined earlier. Right? It was actually a definition. I'm writing it again. And then once I know this, this part, this inner integral is precisely s sub t phi of x. And that's what I have here. Right? All right. When does this happen? As t goes to infinity. Fix an s, fix any s. Then can anyone tell me where it converges to as t goes to infinity? It's the same thing, right? Right. If instead of saying t goes to s, right? If t goes to s, t plus s goes to s, and conversely. So it also goes to the same limit. Okay. What do we know about st plus s? It's a semi group, right? You got to help me because I automatically want to say semi-martingale. Okay, that's not what I want to say. So S sub P is sub S P of X nu dx converges to this. But is this what kind of a function is this? S sub S phi. Feller, right? Phi is continuous bounded, so it's also continuous bounded. That's the definition of a Feller semigroup, right? So for this, if I call this as psi, let's say, then S sub T psi of X nu dx, where would that converge to as T goes to infinity? So it would also converge to, right? If you call it like this, okay? The same thing I have written as psi is S sub S phi. It's also a continuous bounded function thanks to the Feller property, and it would converge therefore to integral of psi mu dx. Whereas what was this limit? So a sequence cannot converge to two different limits. So these have to be the same, correct? Now instead of psi, I can put it as S sub S, right? So these guys are equal, right? This is equal to this. Now look at the equation star that we wrote for invariant measures. The equality of these two boxed items is precisely the definition of invariant measures. Mu is an invariant measure provided these two boxed items are equal. And S was arbitrary. And that's it. So I just wanted to give you some confidence, right? First time if you look at it, it's threatening. Second time less threatening. Third time it's friendly. Fourth time you will say, oh, it's trivial, right? So that's how as right. We used to, even as a student, when I was a student here in Chennai, we also got into this bad way of writing, part A is obvious, part B is trivial or something, Then professor used to get furious. So and that finishes the proof, right? So the equality of this is precisely the meaning of mu being an invariant measure. Likewise, you can also prove that if there is weak convergence of mu t super x, let's say, you don't start with the mu and all that, mu t super x, if it weakly converges to mu is a unique invariant measure. If this weak convergence happens for all little x, all right? I'll state it later. Okay, so time flies. And next I will state this theorem is difficult to, the hypothesis is too strong. If you have actually the solution of a nonlinear PDE or something perturbed by noise, the distribution of mu sub t is kind of scary, right? You wouldn't know what it is. It won't be Gaussian or log normal or whatever. You cannot say anything about them, right? So we need to get something that's more easily verifiable, all right? So the theorem is due to Krylov and Bogolyubov. So once you verify the condition in this and then say that there exists an invariant measure, you can call it as a Krylov-Bogolyubov argument. So When you state that, then later on you may not even show the proof. It follows from Krylov-Golubov argument, like that. So what it says is, again, let ST be Feller. For some x, member of E, let there exist a sequence Tn increasing to infinity such that 1 over Tn, these measures, okay, I got to use this x, right? And then I'll do some E or S, I don't know. T. Everywhere there is T, so I'll put an S. T of S dot ds. Such that these measures are tight. Such that the sequence of measures is tight. What is tightness? Tightness is simply another word for, you knew? Relative compactness, right? In the space of probability measures, you need relative compactness, right? Tightness being equivalent to relative compactness in the space of probability measures with the topology of weak convergence, right? That's called, whose theorem is it? Prokhorov, right? That's an important theorem to learn. Anything about compactness is very important to learn, starting with the Heine-Borel theorem, right? All the way, right? And Sri was also telling today about, compact embedding. Professor Adimurthy talked about the Relich-Kondrashov theorem, right? These are all very important. Huh? And if you want compactness in LP spaces, it's a theorem due to Kolmogorov, huh? Things like that. So all these compactness theorems are important because all we can get are a sequence of approximate solutions or so, right? And you want at least along a subsequence for them to converge, right? You may even get just boundedness of the subsequence of the sequence. Therefore, you need some compact embedding to say that you can actually pull out a subsequence. Huh? So, tightness is actually in the space of probability measures. You have to be more. You have to visualize more complex things, right? So first there were numbers, right? First there were integers, and then right. Slowly there were irrational numbers, the whole set of numbers, complex numbers, function spaces, right? Now this is a space of distributions, right? Probability distributions, and the topology is always weak convergence for us right now. So tightness means they are all kind of boxed in. Much of the measure is in a compact set, correct? Except some epsilon, the rest of it is all contained in a compact set for all these measures. So that's tightness. Then how would you prove that all of these are actually tight, right? If given a solution of a PDE, stochastic PDE or ODE, all you do is convert this, you can actually find some moment estimates, and from the moment estimates you can compute, you can say that these are all within, right? So first idea is always to get some a priori estimates, and then to get that there is tightness, you will just say probability that these measures actually live in a compact set is less than or equal to, and so on. You'll use the Chebyshev inequality, which is actually the world's most trivial inequality, right? But then it's very useful, and then say that it all goes to 0 and stuff. Okay, then there exists an invariant measure. For ST. So I won't have time to prove this, because if I prove this, that's all I would do. So maybe we can, this is a very nice proof. Again, we will cordon it off and do it in the tutorial. Okay, so this is also left as an exercise. But then you can see my notes, which I have posted, right? Which has some misprints, but you can modulo misprints, it's correct. And I will correct them. I can correct them anytime, I'll do it. But right now you can look at it, it's more or less correct. Okay, another thing. Next. I'll define what is known as ergodic measure. Okay? So, definition. That's what we were going for, right? Namely, now existence is over. And so, the set A is called invariant for the semigroup for ST. We know that it is a semigroup and all that. If ST means for the whole thing, right? For the dynamical system. Okay. If S sub T acting on indicator of A is indicator of A. And so now I got to define what is called the ergodic measure, all right? But I'm just gonna, I need another statement here. Let mu be an invariant measure. Invariant measure for ST. Okay, so maybe the definition starts here. So this is to be true, mu almost surely. Then it is called as A is called an invariant measure. Okay, so that's one part of the definition. Second, mu is called ergodic. If mu of A is 0 or 1 for all invariant sets. All right. So this is an equivalent definition of ergodic. You can either say that the time averages should converge to a phase space average, or in the almost sure sense, or you can also say that mu of A is 0 and or 1 for all sets A which are invariant. Okay, for all invariant sets A. Let's take this to be the definition. Then there is a theorem, a standard result, which says the following. We won't prove this. I'm just giving you, this is the longer proof. If mu is ergodic, then for all phi member of L2 mu ST phi phi of x and so on, okay, mu dx. So one thing that before I rush off, I want to say that mu has to be an invariant measure before you say that it is ergodic, right? First you got to therefore show that there exists an invariant measure and then prove a statement like this. But such a statement cannot be proved easily because you don't know which sets are invariant and so on, right? Of course, in the strong law of large numbers case, the invariant sets will be tail events and so on and so forth, okay? So this will converge again in the L2 of mu sense to integral of phi of x. Here I was not actually correct. It's not mu dx, it's dt. D here, as t goes to. Sorry about putting t in the integrand as well. So that's really the a theorem akin to what von Neumann proved, right? But then he didn't assume that mu is ergodic. Okay, so okay. Now we will just pause and think about one small result, very useful, about the structure of these measures that we get. Suppose we get two ergodic measures, all right? You all understood, right? In the Hamiltonian dynamics, the ergodic measure obtained would have been purely in the constant energy surface, right? Because the Hamiltonian was 0 and therefore it cannot, energy doesn't change with respect to time. Well, I said that an hour ago, you might have forgotten. And therefore there are two ergodic measures, maybe their supports are disjoint, right? So they will be at least mutually perpendicular, correct? So that's what I'm going to write here. Mu and nu are two ergodic measures. So slowly I'm going around telling you the minimal theorems that are statements that are necessary to find suitable sufficient conditions for you to prove existence of an ergodic measure for a large class of dynamical systems. Are two ergodic measures. For ST. Then mu is perpendicular to nu. What does mu perpendicular to nu mean? Means they don't talk to each other, right? They're enemies. And you know about perpendicularity, singularity of measures, and absolute continuity, and so on, right? Have you all seen that? Have you all done Radon-Nikodym derivatives? Okay, you will see it, but then don't worry. I'll just say that in this one, I'll actually prove that mu and nu they live on separate sets. All right. So if this is the state space, if this room is the state space, one measure lives somewhere here, there is another one lives there. So they're kind of, this is what I mean by mu and nu are singular. Singular is not the word. What is the word? Singular. That's the word. Okay. Proof. How does one prove this? Let me think about it. So you want mu and nu to be singular. So take an A. such that I said they are ergodic, right? Take a set, okay. Let A be an invariant set. Give me a second. Let mu and nu be two ergodic measures for ST. I had to say that mu and nu are different, okay? And mu is not equal to nu. That's what I was missing. Then let A be such that mu of A is not equal to nu of A. Right, take like this. Then from this theorem, from previous theorem, instead of phi, phi is allowed to be in L2. Therefore, I'll take indicator of A. All right? 1 over t integral 0 to t indicator of st indicator of A, S sub s indicator of A of x, okay, ds. Here I said that if mu is ergodic, it converges to integral of phi of x mu dx, right? So it will converge to integral indicator of A of x. So indicator means characteristic function. You all know that, right? So a characteristic function is used by mathematicians in general. If you are a probabilist, you use indicator functions, right? Okay. Or if you are a harmonic analyst who was originally a probabilist, you use indicator. It's the same meaning. That's in L2, right? But then along the subsequence, which I didn't show you here, right? It would converge if you want. Right? You can pick a subsequence such that this happens almost surely. You all know, right? Even L1 convergence is enough, right? Even convergence in probability is enough. Things like that. So, what is the meaning of this? Indicator of A mu dx is just another fancy way of writing mu of A. And this is happening almost surely means it is with probability 1 as measured by mu, right? Okay. What else happens? S sub s indicator A, the same thing, right? Will also go to nu of A, right? You can pick, let's say, a common sequence for which convergence happens almost surely in this way. But mu of A is not equal to nu of A, right? So this almost sure set here, the almost sure set engendered in the first part, call it as B. The almost sure set that's obtained here, call it as C. All right? I'm not writing too much because only time flies, right? I think this is relativity of time. Namely, time flies for me, but I'm not sure how it is for you. Okay? So, mu of B is 1. Nu of C is 1. Because here mu is the underlying measure, here nu is the underlying measure, right? And B intersection C is empty. Because it cannot be converging to one number and another number simultaneously, right? So that's the idea. Yeah. Oh, B is the almost sure set. Yeah, I called it as B. Right. I didn't write fully. But then it's all there in my notes that I posted, so you can look at it. I'll revise, I'll make it cleaner, right? And then put some more things and again I'll upload it. Maybe Professor Manna will help me with it.
here of the intersection is 0 on both.
Right. Yeah, okay. That's enough, right? So that means, what does that mean? Well, I can also write B intersection C to be.
mu of B intersection is equal to
Yeah, right, like that, right? That's why I wrote it generally, right. Mu of B intersection C is nu of B intersection C. Is that what is that? Right, that's the correct way. Yeah. Okay, so that's the thing. Next is about, I'll just introduce a concept and leave you there, and then we'll continue it tomorrow. Definition. Remember, Boltzmann postulated that if the orbit goes everywhere, right, then there should be ergodicity, right, ergodic behavior. So you would also recall that Professor Nandakumaran, okay, he talked about the exact controllability or null controllability. Here in probability theory, we cannot do that, right? Because it really underlying is a parabolic equation. So you can only talk about approximate controllability. You can get somewhere near, right? You cannot exactly hit a point. So that's the idea of irreducibility. Markov chain, sorry, except x indexed by x, right, is irreducible if for any x member of E, G, any open set in E, and for any x and G and T greater than 0, P sub x, that is you are starting at x, then in time T you want to go to G, that's positive. You cannot say with probability 1 and all that, right? So then we call it to be irreducible. Okay, what else I need to say?
So trajectory must always enter
That's right.
positive coordinate on open sets.
That's right. And that happens even with the two-dimensional Brownian motion, right? For instance, it will go arbitrarily close to any point. And that can actually be used to prove Picard's little theorem and all that, and Casorati-Weierstrass theorem about isolated singularities and so on. So that's the main idea behind those. And so this is precisely what how we can translate Boltzmann's idea about going everywhere, right? Irreducibility. Now the final result that I would like to prove this to you because it's first of all short, so I can actually prove it. And I'll do it tomorrow, but I'll just state the theorem, final theorem, after which we can go to stochastic PDEs. The theorem is, I don't want to write too much. So, irreducibility, a strong fella, implies ergodicity. Of course, you always need let mu be an invariant measure. If you want some more English, I can put them so that it's easy to read. So this is these are actually conditions which you can verify, all right? And irreducible